means this. Carbon plus oxygen gives you carbon dioxide. Okay, so which means that you have a reaction going on. There are a few things you need to understand about this reaction, so we'll write it in detail. These two things on the left-hand side of the arrow, these are called the reactants because they are reacting together. And then whatever you have on the right-hand side of the arrow, they're called the products. This arrow is called yield. Yield meaning reactants give products. Reactants yield product. Okay, that kind of a thing. You will never write this equation like this. Don't write it like this because the left-hand side is not equal to the right-hand side. Okay, chemically speaking, they're not equal. Okay, because on the left-hand side you have carbon and oxygen, on the right-hand side you have carbon dioxide. Okay, so they're different. So we always write an arrow. So please make sure that you don't write an equal sign ever in chemical equations. All right, so that doesn't work. This is the first aspect of writing any chemical equation. Okay, the second aspect, if we write this equation again, or different color. You remember these symbols? They are easy to remember, okay, from last time. And that's it. Carbon is a solid, oxygen is a gas, and carbon dioxide is a gas as well. Okay, so it tells you the state in which everything is in. So you can actually get a lot of information from just writing one chemical equation. There is another thing I would like to remind you of, okay, which I said that I will tell you before, later. Okay, so now it's later. Carbon plus oxygen gives carbon dioxide. The oxygen over here that we write is O2, not O anymore. Okay? When you're trying to do mass percents, when you're trying to do empirical formulas, when you're trying to figure out the structure of a compound, then you have O. Then you don't have O2. Then you have elemental O, atomic O. Okay? Now you will have O2. So for all the chemical equations, all your diatomic gases will come in. Okay, so whenever I say we're talking about chlorine, addition of chlorine, that doesn't mean Cl, it means Cl2. Okay, so this is something you have to keep in mind as we go on writing all these equations out. Okay, so far so good? Okay, nothing too critical here. The other part about this equation, okay, that we need to talk about is when we write chemical equations, they should be all balanced out. Okay, because we know from Dalton's atomic theory and even otherwise, we have the law of conservation of mass. Okay, so whatever we have on the left-hand side should be also on the right-hand side. Dalton's atomic theory says that in a chemical reaction, elements are rearranged. Okay, they're not going anywhere. Okay, or you're not creating anything. So which means you make sure that your equation is balanced, which means that you look on the left-hand side and the right-hand side and make sure you have equal number of atoms. Okay, on both sides. So here you have one carbon, here you have one carbon, two oxygens, two oxygens. Okay, not O2 as oxygen, but two oxygen atoms. Okay, that's how you should look at it when you're balancing an equation. Your O2 is O2 over here, but it may be O3 as in a carbonate on the right-hand side. Okay, depending on the reaction. So you can't look at it as O2 and O3. Okay, you have to look at it as two oxygen atoms and three oxygen atoms. Okay, things like that. So, you know, try to keep that separate. So which means everything is balanced. Okay, in here, everything is accounted for, which means that mass is conserved. Okay, which is really what you want from any equation. All right, so the other way of looking at this equation then is from a mathematical perspective, okay, from our chemical perspective, that we have 1 mole of carbon, we have 1 mole of oxygen, and then we produce 1 mole of carbon dioxide. Where am I getting the 1 mole from? The 1 is coming from the fact that I don't have any number in front of this carbon, okay, right now. So I have 1 carbon atom, I have 1 molecule of oxygen, and I have 1 molecule of carbon dioxide. Okay, so that's where I'm getting the 1s from. 1 mole, 1 mole, 1 mole tells me what? That I have 6.02 10 to the power 23 atoms of carbon, 6.02 times 10 to the power 23 molecules of oxygen, 6.02, 10 to the power 23 molecules of the product. Looking at this equation over here mathematically, you would think that I'm adding this many atoms to this many, 6.02 plus 6.02. Maybe I should have twice the atoms here, but that does not happen. Okay, because it depends on the kind of reaction you're doing. You may get twice the atoms, you may not. Okay, the atoms are important, but we're talking about masses also, and let's see if mass is conserved or not. Okay, so how many grams do we have in 1 mole of carbon? Grams per mole, right? Okay, so this is something you're getting from the periodic table. It's nothing that you have to invent. And oxygen is, and you can round it off for me if you want to, it is times 2, because you have 2 oxygens over here, right? So 16 times 2, and that is 32 grams per mole. Over here, you have 1 carbon, 12 plus 2 oxygen, and again 2 oxygen is 32, so that is 44 grams per mole. And so when you add the mass on the left hand side and the right hand side, they both come out to be 44 grams per mole. Okay? And that's how we know the mass is conserved. If you look at it from an atomic point of view, you may not understand it. Mole point of view, yes, you will understand it. Okay? The moles help us to understand how to balance an equation, and then the mass over here tells us, yes, that mass is conserved. Okay? If your equation is balanced, then your mass will be conserved. All right? Except for the last part where we converted atoms into moles and moles into molecules, things like that, you will hardly ever use this number. Okay, I said that before also. Okay, you will hardly ever use this number. It's important to understand that this is the number of atoms you have in a mole. So you understand it, but other than that, we will not use it. Are we good so far? Okay, simple equation. Okay, let me write another one then. And we'll see how we do with that. Here we have N2O5 giving us nitrogen and oxygen. Everything is in gas. If you want to take a minute and balance this, please balance it out if you can. If not, it's okay. I'll get there with you. That's your first task in general, is to write an equation and balance it. Anyone? Yes? Need 2?
In front of the N2O5.
Okay.
And then we put another 2 in front of the N2.
Okay.
And then a 5 in front of the O2.
5 in front of the O2. Very good. Did you start with oxygen or did you start with nitrogen?
I started with oxygen.
You started with oxygen. Very good. Okay, so you got to start somewhere. And N2 was the same before, right? So N2 was N2 here and N2 here also. So there was nothing to balance out. Oxygen was the one that was missing. So here you have 5 oxygens. Here you had 2. So the best thing to do is do the crisscross again. Okay, whatever you have down here, which is 5, you give that over here to make it 10. And then whatever you have here, 2, take it up here to balance that out. Okay, so you have the same multiples then. Okay, at that point. And then whatever number you have here now for nitrogen, you're going to have to balance that out too. Okay, so it's a step-by-step process, and it comes a little bit more from practice, okay, than anything else. Here, I can't even tell you what the strategy is, except for the oxygen part, which was not balanced. But otherwise, both of these are what we consider elements also, right? O2, N2, Cl2, they're by themselves. So if you change anything in there, maybe you'll change the other formula, maybe you won't. Okay, so those are the things that you balance in the end, okay, usually. So anyhow, this is all balanced now. Is everybody okay with this? What does this tell us? This tells us that we have 2 moles of dinitrogen monoxide, 2 moles of nitrogen, and we have 5 moles of oxygen. Good? when you write these equations out, okay, when you balance them out, you may want to say the name also of the compound, okay? Don't just say N2O, try to say dinitrogen monoxide because that will help you with your nomenclature, okay, a lot. Because right now I know you're still learning your nomenclature, so the more you say these names, the more it will become easier for you, okay, and the more practice you will get. Okay, so that's what this equation means, and I'm not going to do the mass, okay, for all of this, but essentially what you have is 4 nitrogens here and 10 oxygens, right? On the left-hand side, okay, of the equation. How many nitrogens here? Again, 4 nitrogens and 10 oxygens. Okay, and so if you have the same number of atoms on both sides, the mass should be conserved, okay, at that point. And that's the whole point of balancing an equation, is to make sure that the matter is conserved, okay? Initially, when I said it's all about the atoms, it is about the atoms because that's exactly what you just did, okay? You balanced all the atoms out. You can't leave any atom out, okay, from an equation, right? Because again, Dalton's atomic theory, okay, that you can rearrange atoms, but you cannot get rid of them, okay, anyhow. So in the rearrangement, you have to account for everything, okay? You can't lose any atom, and so that accounts for the mass also that we have. Okay, let's try another one. And let me give you a word equation now, because this is something you will have to do for me a lot. Hydrochloric acid plus zinc to give zinc chloride and hydrogen. So I'm going to give you a minute to write this equation out and see if you can balance it also. Ready? Dominic, do you have an answer for me? No.
That's what.
Because I'm looking at it and I'm like, they're balanced. I forgot the two.
The zinc chloride. Zinc is always +2. Remember that. Okay, yeah, from the periodic table. Write that down. And then hydrogen is always going to be written as a diatomic. So it's H2, not just H. Okay. Zinc is a metal. It's an element by itself. So you can leave it like that. And then HCl, of course, is the acid. Okay, and if I want to be totally thorough about everything here, I would write AQ, I would write solid, I would write AQ, and I would write gas. And right now, at this point, some of these things may be a little hard for you. I'm not expecting you to write me the states of all of these things, but at least you should be able to write the equation. If you don't write the state, it's not going to hurt your equation. Okay, so the important thing is knowing the elements, knowing the compounds. Yes, Jackie?
Why was the hydrogen H2 again?
Because it's a diatomic element. That's how it exists on Earth.
Oh, okay, yeah, because we're referring.
Yeah. Okay. Did you balance it out? What do I need? 2 in front of HCl. And are we happy now? Yes, we're happy. Okay. This is called a word equation, by the way, okay, where you have the names given to you and not the formulas. And again, I'm very sorry to say, I'm usually very kind, but I'm not that kind, okay? So usually I will give you only a word equation, and you will have to figure out the formulas yourself, okay? Which is where your nomenclature comes in, because I really want you to know the nomenclature. Okay, write me one more. And nitrogen is? Hydrogen is?
H2.
And ammonia is?
NH4.
NH3. Yeah, that's what
Ammonium.
I thought.
Ammonium is
NH4. Ammonia is NH3. Ammonium is NH4 plus, which is a polyatomic ion. So NH4 plus, that's ammonium. Ammonia is on NH3. Okay, so yeah, it comes from the same things. Is this balanced? So what we're going to do is balance the nitrogen first, right? So 2 down here takes to 2 up here, and then we have 6 hydrogens, and so 3 goes up here. Okay? All right. So now this is 1 mole, this is 3 moles, and this is 2 mole over here. The numbers that we are using to balance the equation, these numbers that we're writing, all these numbers, they have a specific name and they're called coefficients. If you don't write any number in front of any element, like here, the coefficient is 1. Okay, if there's nothing there, because at least you have 1 molecule of it, and that's why I like writing the 1 mole. Okay, I like to think things in moles, because then I know that my coefficient is 1. Over here, this is 3 in front of hydrogen, so I have 3 coefficients and 3 moles, and my coefficient here is 2, which is then 2 moles. Okay? All right. The first task usually is to write these kind of equations out and balance them. You're practicing for balancing equations is in chapter 2 because that's where it was. Okay, in this chapter and not in chapter 3. Okay, and so, but we are in chapter 3 now. Let me give you a handout, which you're going to work on your own. You do not need to submit this to me because I have other grading stuff that I need to do.
What's the reason for N2 the same as the oxygen?
Yes. Yeah, there are only 7 diatomic gases.
Okay.
Yeah. Okay, just take some, pass them at the back. And then here. And you can bring the extras later, no problem. But what this is, and again, all of these worksheets are online also. If you miss it or if you want to do it again, most welcome to. All these are word equations, okay, for you. So write the element out, balance the equation, okay, those kind of things. Let me just give you some clues about balancing equation. Otherwise, you go with kind of what I just said to you, okay? You find what is not balanced in there and then start from there. If you have something like this, okay, with the zinc, hydrochloric acid, let me remove the 2 from here first, okay, and then let's talk about this. So once you have everything correct, and by the way, yeah, if your nomenclature is not good and your formula is not correct, everything else is going to be wrong, okay? And then not only everything is going to be wrong, your balancing may turn out to be wrong also, okay? So please be careful that you know your nomenclature well. So here, your instinct, once you see the formula like this, your instinct is, okay, you know, I got 2 chlorines over here, I only have 1 chlorine here, I have 2 hydrogen here, I only have 1 hydrogen here. I would always start with a compound, okay, to balance an equation, because once you change one compound, you will change another compound also, okay? So change the compounds first. That's the best thing to do. You leave the elements to the end, because I can put any number in front of zinc is not going to change any other number, okay, because it's by itself. So I can use that for my last thing to balance out, okay? And that's why I look at H2 also as a compound and not as an element, because in some cases, like HCl, I only have 1 hydrogen, okay? On the other hand, there I have 2 hydrogens. So which means that if I change the quantity of my H2, I would also change the quantity of my HCl, okay, over here. So think of those as compounds. Zinc, standalone elements, zinc, magnesium, things like that, you can balance them at the end. Okay, so that you don't have to worry about it. So the first thing is to find whatever is completely not balanced and then go from there, okay? And eventually, you just learn how to do these things, okay? Any questions? No. All right. So now I'm going to take you to another thing called stoichiometry, which is the next large part of this chapter. And I'm going to use this equation because this is a nice equation. So 2HCl plus zinc to give zinc chloride and hydrogen. Again, as I said, in this case, if you don't write the states of the matter, it doesn't matter. If it is given to you, that's fine. If it's not given to you, it's not going to change anything as far as balancing is concerned. In the next chapter, we'll really get into it. This chapter, it doesn't matter. Okay. One of the things about stoichiometry, okay, is that this is about a chemical reaction. A chemical reaction means this is a process by which you're trying to make something. Okay, so for example, in this reaction, you have two reactants. You have hydrochloric acid and you have zinc as your reactant. Your products that you're forming is zinc chloride and hydrogen. Okay, do you have any control over what kind of products do you form if you have these two starting materials? No. Okay, you don't. And that's the thing that we do in research labs, is to make sure that we use the kind of materials that we need in order to form a product so we don't waste anything. Okay? So for example, and I always do this, sandwiches, and I'm sorry if I make you hungry, but if you make sandwiches, how many slices of bread do you need? Please tell me 2, right? Okay, not 3. All right, good, because that would be like a huge sandwich. Okay, so let's go with two slices of bread, okay, for a sandwich. What else do you need? Right. Okay, just make your sandwich.
Lettuce, tomatoes, ham.
Avocado.
Okay. Wow.
Fancy chemistry.
Yeah, I don't need that.
I don't eat
I need
meat, so
something that is
Bacon.
I need something that's measurable. Okay, very good.
Cheese.
Okay.
1 slice of cheese.
condiments.
I can take avocado too. Okay, or condiments, whatever you need, okay? All right, so let's say you need 2 slices of bread. Maybe you need 2 leaves of lettuce. Maybe you need 2 slices of tomatoes. Maybe you need 1 slice of the cheese and maybe 1 slice of avocado, okay? That's what you need to make 1 sandwich, all right? Now, is it possible that when you go to the store that you will actually get 2 slices of bread? No. You will get a whole loaf of bread, right? So in that loaf of bread, you can have up to maybe 20 slices, okay, of bread, which means that if you only wanted to make 1 sandwich, what happens to the other 18 slices?
You have to balance them out.
It's not balanced, right? Because technically speaking, if you're just making 1 sandwich, either you keep that for later or it goes waste, right? That's part of stoichiometry, okay? All right. 2 leaves of lettuce. Can you get 2 leaves of lettuce? You need the whole head, right? Okay. Again, you will take those 2 leaves out and the rest of it then is waste, okay? All right, 2 slices of tomato. You see where I'm going with this, right? Okay. So maybe 1 slice of cheese, which is also not possible because you only get packages of 12 or 24, right? And so then you will get the 1 slice from there. So that's how these things work, which means that if you wanted to have 1 sandwich and you buy all the raw material for all of this, just to make 1 sandwich, can you see how much wastage you created just now? Okay? How much money did you put in there? You put a lot of money in there, isn't it? Okay. You put a lot of money, you got 1 sandwich out, and then you threw away all the other material. Why? Also because this is produce, which means it does go bad, okay? Now, if you were making 5 sandwiches, is that a good deal? Maybe a little bit better than 1 sandwich, okay? Or if you were making 8 sandwiches, maybe this would be a better deal. Do you see what I mean then? Okay, so but if you're making 8 sandwiches, then you would also need maybe 3 or 4 tomatoes. Do you see that? Okay, that is stoichiometry, okay? Trying to figure out that if you want to make 1 sandwich or if you want to make 8 sandwiches, then what are the quantities of material you need, okay, for it? So, and I want you to take that whole thing and put it into this analogy over here with this reaction, that if you have HCl and zinc chloride and hydrogen as your products, and you wanted to make 5 grams of hydrogen, then how much of HCl will you start with and how much zinc will you start with? Do you see? That's the thing, okay? Or you can say it the other way, okay? That if you had so much amount of hydrochloric acid and so much of zinc, how much of the product will you get? Okay, that's what we're talking about. So every day you do stoichiometry at home. Okay, whenever you cook, whenever you do anything, you do stoichiometry all the time. You just don't relate it to chemistry yet. Okay, but in chemistry you really have to do this because what happens in chemical industries is if you want to make hydrogen, which hydrogen gas is, it's a very consumable item. So if you make hydrogen gas, okay, over here in an industry, and you need a certain amount of zinc and hydrochloric acid, then you want to make sure that you get the right amount of material, okay? Because if you don't get the right amount of material, either you're short or you're wasting material, okay, in there. So you want to make sure you get the right amount. Okay, so supposing, just like the sandwiches, supposing you were making one sandwich and you bought all of that stuff and you wasted everything else, what happened? You lost a lot of money, right? Whose money was that? Yours? Maybe mom, dad's? Okay, I don't know. Okay, but it was somebody's money, right, that went. The same thing happens with chemical reaction. All the industries that are out there, all the chemical industries, food industry, pharmaceutical industry, those people are not making products for themselves. They're making products for everybody else, right? The consumers. So what happens then? The prices will increase, okay, for you. If a process is not efficient, if they don't do proper stoichiometry, and they don't use their starting materials efficiently, if their reaction is not efficient, then your prices increase for you, okay? That's what happens. In any case, that's what we're talking about here, okay, is that if you use everything efficiently, then you make products efficiently, and then you don't have to charge the consumers that much, which means that consumers will buy more products also, which is good for the industry, okay, in some ways. Besides, chemicals are much more dangerous to throw away than lettuces, okay? Yeah. It's a lot more dangerous, it's a lot more toxic, all right? So it's a lot better to consume those chemicals, not just in your starting materials, but even the product. So let's see if you're doing this reaction. You needed only hydrogen gas, you don't need the zinc chloride. So what happens to zinc chloride? It's waste then, correct? If you don't need it. So which means you either find use for the zinc chloride or you throw it away. And if they're throwing it away, they're not getting money for it. So again, who's paying for it? We are. Yes, we are paying for it. Okay, so that is your basis for stoichiometry. Now we have gotten into what's called green chemistry. It's one of the latest things. It lasts about 10, 15 years old. And green chemistry is kind of a very efficient way, green way of making products, which means that they try to minimize all waste possible. Okay, they try to use natural products as much as possible. They try to use enzymes and biological agents in order to do the processes. So that way they don't have to work with elements and dangerous chemicals and catalysts. And then even the products that they end up getting sometimes are actually biodegradable. Okay, so a lot of your laundry detergents, a lot of your materials that you have, those are all recyclable now. Okay, a lot of it, and that's part of green chemistry. The basic concept of green chemistry is what they call atom efficiency, and atom efficiency is that whatever you input, your output should be completely usable. Okay, that's atom efficiency, and that's green chemistry. But we're not going there. Okay, we're still sticking with stoichiometry over here. But do we understand the concept then? We're okay? Maybe I spoke too much. I don't know. Okay, all right. Let's go back to the equation, and let's write 2 moles, 1 mole, 1 mole, and then 1 mole. This is our mole ratio. This is kind of like making the sandwich, where you decide how much of something that you need in order to carry out this reaction, okay? We're going to carry out this reaction to as efficiently as possible. We have to do calculations, okay? And again, remember, you cannot go to the lab. You cannot weigh out 2 moles, can you? No, okay? There is nothing like weighing out 2 moles. So which means you have to convert everything into grams, all right? And you know how to do that now because you know the periodic table. Okay, so from the periodic table, you figure out how many grams everything has, and then you calculate from there. And again, things are not as easy. Okay, as it says, so zinc, for example, is 65.39. So we will probably never use 65.39 grams per mole of zinc. Okay, which means that we will never use this much of zinc. We will probably use 1 gram, 2 grams, okay, of zinc. So which means if you're using 2 grams of zinc, how much hydrogen will be produced from there? So you can calculate that, okay? If you're using 2 grams of zinc, how much HCl do you need in order to make sure that all of that zinc is consumed, okay? That is stoichiometry. That's the calculations, okay, that you end up doing in stoichiometry. All right, I'm going to take it very simple first. Before we get into grams, I'm going to get into mole ratios, and hopefully this will help a little bit. If I use 1 mole of HCl, how many moles of zinc do I need? Half of that, right? Because I just have this. So if I have this one, then I also have to have this one, okay? Because that's the mole ratio. The mole ratio here is 2:1, okay? So if I have this, I also have this, and then how much zinc will I produce? Zinc chloride? Half of that, so which means that, and how much of hydrogen again? Good? That's the mole ratio that we're talking about, okay? All right, so that's one option that you can have. I can also do it another way. I can say, okay, forget this one. Maybe I just want to use 0.25 moles of zinc. Instead of 1 mole of zinc, I want to use 1/4 of it, okay? So if I'm using 1/4 of the zinc that I should before, so if I have only 1 mole, and I'm using only 1/4, how much of HCl will I need? How many moles of HCl?
Okay.
Do the mole ratio. Tell me in moles.
Half of one.
Half of 1. Tell me the number.
Wait,
0.5. Thank you very much. Okay. The ratio is 1:2. Okay? The ratio is 1:2 over here. So this is 1 and this is twice of that. So if I have 0.25, all I have to do is twice of that. Okay? You don't have to look at these numbers that way. Just look at the ratio of it. Okay? The mole ratio of zinc to zinc chloride is 1:1. Okay? So if this is 1:1 and I'm using 0.525 moles of zinc, I should get 0.25 moles of zinc chloride, okay, because the ratio of zinc to zinc chloride is 1:1, okay, so I should get the same amount back. Are we good? Okay, and then this one also should be 0.25 moles. And again, these are all mole ratios, and I want you to appreciate the mole quantities over here, okay? And again, I'm very sorry, I am usually kind, but I'm not. Okay, which means that I will not give you moles, okay, to work with. I will give you moles maybe in a multiple choice question, okay? But to work it out, you need to work in grams, okay? Because grams is how we weigh things out, okay? So if you're working in grams, then things are a little bit different because now you'll have to convert grams to moles, okay? That's an additional calculation that you have to do. So it's not that tedious because you already know those conversions. We did that last time. So what you have to do is you have to convert grams to moles and then convert the moles back into grams again to find out something else. Comfortable so far? Any questions with any of this? Okay, then let's do a couple problems for stoichiometry. How much ammonia is produced when 3.20 grams of nitrogen is used? And if I don't write it, please take it for granted that this is in grams also. How much ammonia in grams is produced, not in moles. So this is our same equation we wrote before. Nitrogen plus hydrogen to give you ammonia. Here's another thing that happens with stoichiometric problems. This equation we have written before, so we've seen it, but sometimes you will get equations that you've never seen before, okay? My thinking is that if your nomenclature is good, and if I give you a word equation, you should be able to write the equation out. okay, yourself. In some cases, I will give you the equation because sometimes the equation is a little complicated, okay? So in those cases, I will give you the equation. It is still your responsibility to make sure it's balanced, okay? So make sure before you start with anything that your equation is balanced. If your equation is not balanced, everything will be wrong, okay, in that case. So please make sure. So here, let's balance the equation, which we've done already before, so that's all good. So what I've been given right now is 3.20 grams of nitrogen, 3.20 grams of nitrogen. And my question is, how much ammonia is being produced in grams? I always write out my equation like this so I can clearly see what is given to me and what is being asked of me. Okay, so that way I know where I'm going. Okay, and what conversions I need, what mole ratios I need for this. So then I have my strategy, and of course I'm showing my strategy only because this is the first time we're doing this. You don't have to write this every time, okay? But what we'll have to do is we'll have to take nitrogen, the grams of nitrogen that we have given, convert them to moles, and we'll convert them to moles of nitrogen, of course, okay? And then what we're gonna have to do is what we call the mole ratio of, and let me just leave it as mole ratio over here. And in this case, this specific case, it's going to be nitrogen to ammonia in this case, because my question is between nitrogen and ammonia. Okay, so the mole ratio is going to be between nitrogen to ammonia. And then once I have this mole ratio, I'm still in moles, I'll have to calculate grams of ammonia. That's my strategy. I'm going to put my units first. That's what I always do. I did that when we did conversions also. And I advise you to do the same thing here. Okay, with stoichiometry also is make sure your units are correct first. So grams of nitrogen is where I start with. And remember, each of your arrow turns into a multiplication sign. Essentially, this is what I have. 3 arrows, 3 multiplication signs. Now I have to convert grams of nitrogen to moles, which means this is what I have. Now the mole ratio over here, where am I getting that from? The coefficients, okay? And this comes from coefficients from balanced equation. If your equation is not balanced, it's not going to work, okay? So use the coefficients from balanced equation. That's where the mole ratio is coming from. And if you miss the mole ratio, that's a big miss. That's a big miss. The only time the mole ratio is not going to affect you if it's 1-to-1, right? That's the only time you can get away with it, okay? But I look for it, okay? When I'm grading your work, I look for that mole ratio because even if it is 1-to-1, I will always write it out. Okay, so my moles of nitrogen is up there, so my moles of nitrogen goes down here. What goes up here? Moles of NH3, ammonia. And then the last thing I have to do is calculate the grams of ammonia. So then I have moles of ammonia being converted to grams of ammonia. Any issue with the strategy? It all looks really great over here, and then you go home. Okay, I'm going to give you the numbers so that you don't have to worry about calculating those numbers. So 3.20 grams, that's the nitrogen that you're starting with. By the way, if you look at stoichiometric problems, there's only one number given to you, right? Yeah. Everything is magic. Okay, so which means that you have to come up with all the other numbers. All right, there's only one number given to you. Okay, that is the most interesting thing about stoichiometry, which is kind of telling you that you have to learn the process. Okay, there is no memorization in this. Okay, there is no typical equation in this. Okay, although in the chapter summary at the bottom I've given to you a little bit of how to set this up. But this is how you would set up for everything. But this is not a formula, okay, for anything. This is a very general setup. And so every other number you have to come up with yourself. So here in 1 mole of nitrogen, you will have 28.0112 grams of nitrogen. And this number is the molecular weight. Okay? Not the atomic weight, the molecular weight, because it's N2 and not N. If it was N, I would call it atomic weight. Okay, so this is the molecular weight. My mole ratio now, this is something I'm going to get from my balanced equation. So in front of ammonia, I have 2. In front of nitrogen, I have 1. That's all I have to do. No creations there. And then I have to convert my moles of ammonia to grams of ammonia. Again, I go to the beautiful periodic table, okay, to find out the mass of ammonia, and that's about 17 grams. You can work in 2 decimal places if you want to, okay, for all of these calculations, not 3. 2 is also fine with me, okay? By the 3rd decimal place, I told you, it doesn't make much difference, okay, in your calculations. And also remember that you took a pledge with me in the beginning that you will never put ones in your calculator. Okay, yeah, you have lots of ones in there. So just multiply everything on the top, divide it by the bottom. Or go or however you want to do this, it doesn't matter. You should get 3.9 grams or 3.88 grams. And to satisfy yourself, and it's a really good, it's a really important part, okay, for you to feel happy that you did this, okay, and the fact that you were right, okay, is to go ahead and cancel out all these things, moles to moles, moles of ammonia to moles of ammonia, and then you're left with grams of ammonia, so you know you were on the right track. Okay, so that's always helpful. Although, trust me, if you write it the way I was writing, one by one, top, bottom, you should be fine. Okay, it should not be an issue. Okay, this is very basic fundamental stoichiometry. Let me do one more problem here for you. And we'll take the same equation. And now the question is, how much nitrogen is required to make 5.00 grams of ammonia? So take a minute, look at how I set this up, and you set it up as well. Okay, so you're going to start with, this time, grams of ammonia. So all I would like you to do is just do the units. Don't worry about the numbers, okay? Just set up the units that you would use to calculate this first. You should have this set up by now. It's on the board. Okay. And then your numbers. 5.00. Starting with ammonia, converting 1 mole ammonia, and this is 17 grams of ammonia. Mole ratio. In front of nitrogen, I have 1. In front of ammonia, I have 2. And then in 1 mole of nitrogen, I have 28.01 grams of nitrogen. And the answer is 4.12 grams of grams ammonia, moles, moles ammonia, moles nitrogen, all gone. When you go home and you look at your work and you wonder where you got a number from, that's one of the most confusing thing that happens. Okay, when you do calculations, and especially when in the problem you only have one number given to you, okay, and you don't have any other number given to you, then you start wondering, where did I get all these other numbers from? So always think periodic table first. Okay, that's always your first answer. Okay, your large numbers are going to come from the periodic table because those are probably the molecular mass, okay, of anything. And then the mole ratios, the smaller numbers, are probably coming from the balanced equation. Okay, that's your strategy. How are we? We're good? Okay.